Well, thank you very much, ladies and gentlemen. Welcome to my presentation entitled Protons and the Electrical Conduction in a Floating Water Bridge. At this point, I would like to thank the organizers, especially Jerry, very much for his kind invitation, giving me the possibility to talk to you here today. I'm going to talk to you about the interaction, special interaction between high voltage and water. Now, I'm sure that each and every one of you has learned at some point in your lives that this is not a very good combination. Because if you pour water onto electric machinery, especially some that operates with high voltage, it will for sure break. And if you put high voltage into water, you can die. You all know the famous story of the hairdryer in the bathtub. So it's not a good idea to do that. However, this is a very human perspective. And at this conference, we have heard that taking a view from a different perspective might change things. So I suggest we do that and we take a look at our planet from the International Space Station. And we see here that in our atmosphere, or between our atmosphere and the ocean, the interaction between high voltage and water is common. It's happening every day, almost every minute on this planet, and it's called lightning. And I assure you, if nature does something, nature has had time for millennia to optimize its systems, it makes sense and it's good for something. So I think, even if it's very dangerous, and it is, it's worth to take a look and to investigate this interaction. Now, the special phenomenon I'm going to talk to you about was discovered in 1893 by Sir William George Armstrong. And please let me quote from his paper in the Electrical Engineer. He said, amongst other experiments, I hit upon a very remarkable one. Taking 2 wine glasses filled to the brim with chemically pure water, I connected the 2 glasses by a cotton thread coiled up in one glass and having its shorter end dipped into the other glass. On turning on the current, at that time that was a hand-driven Van der Graaf generator, on turning on the current, the coiled thread was rapidly drawn out of the glass containing it and the whole thread deposited into the other, leaving, and this is important, leaving for a few seconds a rope of water between the lips of the 2 glasses. Now in this video we see a recreation of this experiment. We have 2 glasses here, we have a cotton thread, and as we turn on our current, we really have a rope of water between the glasses. Our setup nowadays is not so different from that at that time. We take 2 platforms, we put 2 beakers there, we fill these beakers with distilled or deionized water, we submerge 2 electrodes, preferably platinum, from above. We switch on high voltage, DC, around 15,000 volts. Well, if we do that, then we do get a watery connection between the 2 beakers that even remains stable if the 2 beakers are separated by a few centimeters. And more than that, if we put 2 balancers below, we can even monitor the mass transfer. However, much more interesting than this nice animation is to observe the actual phenomena. Now, in this high-speed video, which is 120 times slower than normal speed, you can see the 2 beakers. The electrodes are just not in the visible frame, but you do see that as soon as we switch on our voltage, we have discharges here in between the 2 beakers, and you see the water surface is moving, droplets are ejected. This is a phenomenon very well understood in the framework of electrospraying. And after some time, we have a capillary bridge. This is just a droplet hanging between the rims of the 2 beakers. And this capillary bridge is the starting point from which the actual phenomenon, the floating water bridge, evolves. Once we have a capillary bridge, after a few fractions of a second, you see the whole thing gaining volume, getting bigger, becoming really macroscopic. At this point, the watery connection can have a diameter up to a few centimeters, and you have a real macroscopic connection between the 2 beakers. Now, in real time, this whole thing happens very fast. You switch on the voltage, the water jumps up, it forms the bridge, And now, as I showed you in the animation before, if you pull one beaker away, this connection remains stable. And even with your naked eye, without any scientific instrument, you can see that this bridge shows properties of two different states of water at the same time. It is rigid, it doesn't fall down. On the other side, and it looks a bit stiff, but on the other side it's highly dynamic. It's changing its diameter constantly, it's oscillating. And if you look at the level in the beakers, you see that one level is going down while the other level is going up, so there's obviously some water flowing through the bridge. So even from a macroscopic observation already, you can see that it seems to be both liquid and solid at the same time. The maximum elongation that you see here in this video is about 2 centimeters. In the meantime, we have reached almost 4 centimeters in length, but this isn't about length, so I think a 2 centimeter video will suffice. And it's very dangerous to go to 4 centimeters because you have to go to 40,000 volts and higher, and I wouldn't recommend it. Now, in order to understand the phenomenon, you can approach it from two sides. Macroscopically, you can consider water just as a medium. You can calculate your electric field or your electric displacement, the field in the medium, in order to see whether it would make sense from an electrohydrodynamical standpoint that this actually can work. And it does, because you see the highest points of highest field strength are here at the edges of the beakers. So you have forces that are pulling the water molecule, which is a dipole, towards these points into the bridge from the beakers and from the bridge back into the beakers. And even if the bridge wants to break down, you see there's a gradient here which is trying to keep the bridge up there unless it is too heavy. On the other hand, you could ask the question, microscopically, is it still water? Is it the same? Or is there a difference? Well, we have applied many methods. The most successful so far was the ultra-fast vibrational energy relaxation investigation. What did we do? We measured the OH vibration of an HDO molecule. So, you all know water consists of light water and heavy water, and in the mixture you inevitably also get HDO molecules. Spectroscopists like HDO because it's asymmetrical, which means that you can excite selectively just one stretch vibration, the OH. And why would we do that? Well, consider me as the HDO molecule. If this is my vibration, this is my hydrogen here, it depends on how well this hydrogen is connected to the surrounding, makes the time it takes to relax. So in liquid water, this will take a very long time to relax because it's very loosely bound. And in ice, this will be very fast because in ice the hydrogen bonds are very strong. Which means that from this relaxation time, we get an idea about the strength of the hydrogen bonds in our system. Now, to put some numbers onto these explanations, ice at 0 degrees Celsius, just normal ice one, has a relaxation time of about 384 femtoseconds. If you melt that ice and keep the temperature the same, the time goes up to 740 femtoseconds. In between there is nothing because that's the so-called phase transition. If you cool down the ice, the time gets lower. If you heat up water, the time increases. If you put some impurities into the water, the time increases as well. So it's literally impossible to get water with a relaxation time between 740 and 384 femtoseconds. Except for the water bridge. In the water bridge, we found a relaxation time of 630 femtoseconds, which means that the hydrogen bond strength in the bridge is in between the liquid and the solid state, although the temperature is much higher, it's 25 degrees or even warmer. It's a little bit more liquid than solid, it's closer to the liquid side, but nevertheless, it is clearly a new state on a microscopic scale, a new state of water, different from the states that we know. Well, how do we get to this state? Well, we can say, yeah, you apply a very strong electric field and thereby the state is induced. This is wrong. Because if we only apply the field and we have no electrical conduction, we have measured this, we don't get the state. Water stays just liquid and you have the normal relaxation times. Now you need to have some current going through the system. You need the formation of an actual bridge to get this new state of water. How does this electrical conduction work? Well, so far we didn't know, because conventionally, electrical conduction in water involves electrolysis. And that means gas production and a local pH change around the electrodes. Now, in a typical water bridge experiment, we don't observe any gas production. This is a very short video, but just to give you an idea, yes, we have the water bridge, we have 2 electrodes here, but we don't see any bubbling at all. Let's quantify the question. How much gas production would we expect if there was electrolysis after all? Well, that's very easy to calculate. All know Faraday's law. We take some typical numbers, 500 micrograms over 30 minutes, Faraday constant. We remember the volume of an ideal gas at 25 degrees Celsius. We consider oxygen and hydrogen ideal gases, and we get to volumes of 91 and 183 microliters. If those gases would form bubbles at the electrodes, there should be 174 oxygen and about 350 hydrogen bubbles. If there were 1 millimeter in diameter, which is a big bubble, so if there were smaller bubbles, there should be even more. So at 1 bubble every 10 or 5 seconds, or even more. So this is something we should see. But I assure you, I have run experiments for 9 years now. You don't see that if you use noble metals. You don't see any bubble formation if you use platinum. I can tell you why we don't see that. In order to explain that, we have to remember that in the water bridge, the situation is not the same as in a conventional electrolysis situation. In this Schlieren image, you see that there's a constant flow of water on the top, on the surface, down the electrode, back into the bulk, and that is true for both sides. So the water next to the electrode, next to the surface where the actual bubble formation should occur, is never standing still. It's always in a flow. What does that mean? Well, if we have such a flow, the bubbles could be detached in a very, very, very small early state. When they're very small, you never see them, and they get dissolved into the water. Well, then you could say, well, if that is true, it will be very quickly saturated, and then we should see bubble formation. Well, no. Because all water that goes here along the electrode very quickly is transported through the bridge. And the bridge is significantly warmer than the water in the beakers. We're talking about 10, 20 degrees Celsius here. And the solubility of hydrogen and oxygen in water is strongly temperature dependent, which means that every small amount of gas that's dissolved here is degassing here in the bridge. So you never get saturation, you never see any bubble formation, but nevertheless, you could produce hydrogen and oxygen. It's a nice hypothesis, but that's no proof. In order to prove that, we constructed a special setup with a nice glass dome, everything airtight. We flushed it with nitrogen. We took samples measured in a gas chromatograph in order to make sure it's only nitrogen in there, and then we let the water bridge run for 100 minutes. And then we took a sample again. And voila, after 100 minutes, we got nitrogen, oxygen. You could say, well, that was leaking in from outside. But we also got a significant measurable amount of hydrogen. Now we measured 0.88 milliliters. We calculated there should be 0.84 milliliters, but in the calculation we assumed that the distribution of hydrogen throughout the dome would be the same, which is not likely because it's lighter than nitrogen. It's supposed to accumulate on the top, meaning that we expect slightly higher concentrations. So, after all, we have shown that hydrogen is produced, so the electrical conduction in the water bridge is electrolytic. It's the formation of hydrogen and oxygen and of protons and OH minus in the solution. Going back to that, we should expect a pH change, because in the electrode reactions, on the anode where we create oxygen, we create protons, and hydroxyl ions are created at the cathode side. It's again very straightforward to calculate how the pH change should be after 30 minutes locally around the electrodes, and it should be pH 2 and pH 10. That is never reached. We never have that. The pH almost doesn't change, which is the reason why for years we have believed there is no electrolysis. It's a little bit more acidic in the anolyte and remains practically the same in the catholyte. Why? Well, another experiment which you have seen perhaps in one of my former presentations gives us the answer to that. It's thermography. Thermography nicely showing that the water bridge emits infrared light, it's heating up, and it does this in a nice pattern. You see that there's probably some sort of hot core where colder water is flowing around, creating these beautiful vortices by mixing with this water. Now, 2 years ago, we published a paper where we showed that when you take a spectrum of that infrared radiation, you see that there is an additional peak that is non-thermal in origin that comes from traveling protons. We've come up with the idea, with the help of Willem and Freund from NASA, that in the water bridge there exists a proton conduction band. And we even calculated the energies, and these energies fit very well with the observed spectral feature here. But what we never said in that paper is, where do these protons come from? Of course, protons are ubiquitous in water, so you don't need a source for them. But I think it's very obvious that these are the protons produced at the anode and neutralized at the cathode. So in other words, we have a flow of water, we have gas dissolving, and we have protons produced at the anode going through the water bridge and neutralizing the OH minus produced at the cathode. Again, this is just a hypothesis. It would be nice to actually prove that directly, and if you have got the right high voltage power supply that can give you enough current so that you can produce a comparable water bridge to the situation without pH dye. So for this water bridge you need approximately 10 milliamps, but then it has approximately the same behavioral thickness as a water bridge without pH dye. You can see, if you look sharply, that around this electrode you get a reddish glow, so there are protons being produced, even though it's difficult to see. And you also see dark blue zones moving downwards here from the cathode and disappearing into the solution. Please contradict me and say something if you don't see that. It's very difficult, but the hydroxyl ions are neutralized so quickly, it's very difficult to visualize it in a better way. I tried to play a little bit with the saturation and to magnify the cathode here. I'm not sure if in this video it's worse or better than in the former video. If I had an actual experiment here, you could watch it with your naked eye, you could see it better, but I think you can see bluish clouds formed here and being neutralized immediately, meaning that protons are traveling from the anode to the cathode, neutralizing all OH minus that is produced here on this side. So In contrast to what I told you 4 years ago, the situation with and without pH dye is comparable if you're creating the same kind of water bridge. If you're using the same current, 0.5 milliamps, with a pH dye, your bridge will be very, very tiny. You will have a much greater pH difference because the bridge is so small, the ion transport, the proton transport velocities are not comparable. But in both cases, you're creating hydroxyl ions, protons, and you get the protons get neutralized here in the cathode beaker. And what you see here are the colors of the pH dye here added after bridge operation, and here during bridge operation you see this is nicely comparable. Of course, we checked whether the pH dye was affected by electrolysis, whether it was electrochemically decomposed. It was not. It's still working, and it was not affected by the water bridge. However, this whole evaluation leaves out the possible influence of other ions. Because we use distilled water, we always think it's just water, there's nothing else in there, so this is the main contribution, period. This is not really true. For the first time now, we have analyzed the water that we use. We are storing our distilled, deionized water in a glass bottle. If you really want to use pure water, this is not a good idea, because if you store deionized water in a glass bottle, you got measurable amounts of sodium, potassium, magnesium, calcium, zinc that is dissolved from the glass. Now, if you run the water bridge in glass or quartz beakers, you see that the concentration doesn't really change, but the ions are concentrated on the cathode side, which is also logical because they are all cations. They're going to the negative electrode. The most important ion is not among those. The most important ion present in our water is an anion, and that's hydrocarbonate. Unless you're working under absolute nitrogen atmosphere from the beginning, so you're buying highly purified water with a nitrogen seal, you're opening it in a glass box, you will immediately have CO2 saturation, and you will have hydrocarbonate. Order of magnitude is about 10 times higher than that of the ions that dissolve from the glass. And there's also been some questions in the past about whether there's platinum being dissolved, although it's noble. Yes, that is true, but the amount is so small, it's an order of magnitude lower than that of the ions dissolved from the glass. And also that platinum is concentrating in the cathode beaker. Now, if you take a look at the contribution of all ions present to the conductivity and thus to the electrochemistry happening in the water bridge, you see that in all cases it's almost 90% of hydrogen, of protons, of ionized hydrogen, of protons, which are responsible for the conductivity and thus for the electrochemical behavior. The water bridge is a proton pump. It's a proton generator, proton pump, and proton neutralizer. 10% is covered by hydrocarbonate. That is also responsible for the slight pH difference you see after switching of the voltage, because the hydrocarbonate ions go to the anodic side, and so you have a slightly more acidic environment there. And metal ions and everything else is less than 2%. We even calculated the conductivities from the molar conductivities of all the ions present in the system, and as you can see in this table, we got very good results for the reference water. We even got the exact same number in microsiemens per centimeter. And from anolyte and catholyte, if you take the error of measurement into account, we also get exactly the values that we measured from our calculations. So in order to summarize, the electrical conduction in the floating water bridge is protonic. These protons are produced by electrolysis at the anode, travel through the bridge, and then neutralized at the cathode. The way how they travel, that is still somewhat open to discussion, from classical transport, going with the flow, Grotthus mechanism, or be it a proton band in the water. Because the current is very low, typically smaller than 1 milliamp, the amounts of gases produced are very small and difficult to detect. We tried with really sensitive hydrogen sniffing devices to look for hydrogen. It's not possible. So if you're running a standard water bridge, even if you let it running for hours, you don't have to be afraid of explosions. The amount of hydrogen is just negligible. Other ions are present, but the role in the conduction mechanism is negligible as well. Now, at this point, I'd like to emphasize that the big guy behind all water bridge research I have been presenting up to this day is Jacob Wojcichlager, my friend and mentor from Graz University. I have to express my gratitude to Lukas Biatkowski and Haupt Bakker from the Amolf Institute in Amsterdam, without whom the measurement of the ultrafast relaxation would have been impossible. Friedemann Freund from NASA Ames came up with the idea of a proton band and protons playing a major role here. I met him in 2009 at the water conference in Vermont. Then we collaborated. And of course, my friends and guys at Wetsus, who did all the actual work here. And next to them, there's a number of people all around the world involved in this research with whom I'm more or less constantly communicating. My thanks go to all of them. Of course, my thanks go to you for your attention. Thank you very much.